Physics and chemistry are often referred to as exact sciences. But the opposite of exact is approximate, isn't it? And approximations are used all the time in both physics and chemistry. An exact science is one that is capable of precise quantitative, that is numerical, expression, and that can make accurate predictions. Oddly enough, only an exact science can demand the use of so many approximations. Physics and chemistry depend on measurements, and measurements are always approximations. The uninteresting exception to this occurs when a measurement involves simple counting. For example, Earth has exactly 2 geographic poles, and there are exactly 6 protons in a carbon nucleus. When Olympic officials back in 2008 gave Usain Bolt's legendary 100-meter Olympic dash time as 9.69 seconds, they were giving an approximation precise to 3 significant figures. If they had stuck a 0 in front of the first 9, 9.69 seconds, that would not have changed the number of significant figures. The 0 would not have been significant. But instead, if they had stuck a 0 after the second 9, 9.690 seconds, that would have implied a 4 significant figure timing. However, the vagaries of sprint timing do not allow accurate measurement of thousandths of a second. So 3 significant figures, 3 so-called sig figs, is the best we can do. But wait, a slightly slower runner might have had a time of 10.01 seconds, say. That measurement has 4 sig figs, and therefore seems more accurate. But of course it's not. The same timing system was used for both measurements after all. This means that measurement accuracy can be characterized in different ways. Sig figs are important, but so is the number of decimal places. 9.69 seconds and 10.01 seconds are accurate to the same number of decimal places. Each is accurate to 2 decimal places. Better said, each is accurate to the nearest 100th of a second. This all seems rather technical and tricky, but it's really not. The key is just to pay attention to both significant figures and to decimal places, and to care about them. Most science students will do just fine if they grasp the general idea here. Something that really helps in understanding measurement uncertainty is scientific notation. A number is expressed in scientific notation when just a single numeral appears before the decimal point, and when the entire decimal number is followed by a power of 10. For example, the speed of sound in dry air at STP, standard temperature and pressure, is reported to be V equals 343.2 meters per second. We say that this is accurate to 4 sig figs. But to see clearly that it's accurate to 3 decimal places, we should write the speed of sound in scientific notation. V sub sound equals 3.432 times 10 to the second meters per second. In kilometers per second, V sub sound equals 0.3432 kilometers per second, which is 3.432 times 10 to the minus 1 kilometers per second. Here, writing this value in scientific notation allows us to see easily that it is accurate to 4 sig figs and to 3 decimal places. That initial 0, by the way, is not significant, but we often include it to make sure that every reader notices the decimal point and doesn't mistake it for a fly on the wall. The biggest challenge in significant figure use involves simple calculation. What happens when we mathematically combine numbers with differing accuracy? For example, suppose we see a lightning flash and then time its thunderclap to arrive 1.8 seconds later. This means that the sound of thunder traveling at 343.2 meters per second has spent about 1.8 seconds getting to us from the lightning. How far away was the lightning? Well, distance equals rate, that is speed, times time. So the distance to the lightning is very simple to calculate. Lightning distance equals thunder speed times the time lag. Lightning distance equals 343.2 meters per second times 1.8 seconds. Here comes the tricky part. Any calculator will easily multiply these numbers for you. Lightning distance equals 617.76 meters. That distance has 5 significant figures. That's impressively accurate. But how do we get a 5 sig fig distance when we started with a 4 sig fig speed and a 2 sig fig time? No way. Our calculator is being careless when it doesn't pay attention to significant figures. Scientists and science students have to be more careful. When using a calculator, think of the input numbers as acting like the links in a chain. The strength of a chain depends entirely on the strength of its weakest link. You are the weakest link. The accuracy of a calculated output value depends on the accuracy of its weakest input value, that is, the input value with the fewest sig figs. So here is the key rule for dealing with the accuracy in any science calculation. The number of sig figs in the output value, the answer, equals the number of sig figs in the least accurate input value. That's both intuitive and easy to remember if you'll think of a chain. We can call it the linkage rule of calculated accuracy. The weakest link determines the strength of a chain. The weakest input value determines the strength of a calculation. In our lightning distance calculation, the weakest input value is the 1.8 seconds of time lag between lightning and thunder. That has just 2 sig figs, so the calculation's output value must be accurate to only 2 sig figs. Lightning distance equals 343.2 meters per second times 1.8 seconds. That's 617.76 meters. That's approximately 620 meters. To show 2 sig fig accuracy properly, I should write the answer as 6.2 times 10 to the second power meters. Then the 2 sig figs are obvious. If I write simply 620 meters, then the significance of the 0 is unclear. However, scientists and even science teachers will occasionally cut you some slack if you don't always use proper scientific notation. What will earn you no slack whatsoever from teachers, and certainly not from scientists, is lying about the accuracy of your answer. If you had left the originally calculated answer of 617.76 meters, you'd have been claiming to know the lightning's distance to the nearest centimeter. That answer is 617 meters and 76 centimeters. But you only know the sound's travel time to the nearest tenth of a second. In a tenth of a second, sound travels over 30 meters. So claiming to know the light's distance to the nearest centimeter is just absurd. And now that you know better, it's an absurd lie. Scientists are obligated to be as accurate as they can be, but not a single sig fig more accurate. As I said earlier, the key is just to pay attention to sig figs and to remember the linkage rule of calculated accuracy. Here it comes again. The number of sig figs in a calculated output value equals the number of sig figs in the least accurate input value. If you'll stop believing all the numbers that your calculator spits out and remember this simple linkage rule, you'll be in good shape. You will not be the weakest link in the chain of scientific accuracy.
See the universe through a brand new set of eyes.